Okay. So it's a bit of a change of flavor, what we're going to do today. So the topic on the, what to the left? Oh, this thing? This thing? I don't know how. This is not a touch screen. Okay. So the topic listed in the sort of the program, school program says small space complexity. But I chose to write the slides, or at least the title slide, as streaming algorithms, because what we will discuss now is more than just a small space complexity algorithm. It's a whole different algorithmic paradigm. So far what you've seen is the random access type of setting, where the input is given to you. So mathematically, that's like on a Turing machine tape, and you can do random access. So in terms of an array, that means you can look up certain positions and so on and so forth and do your computation that way. So in a way, so that's what is usually known as the offline model, okay, or the default model. There are other ways in which an input can present itself. So one of those models is what we will be studying today. In particular, the input can come to you in a stream, piece by piece. The oldest such paradigm is the online setting, where basically you have to make, we are doing the same thing as we usually do for any algorithm, trying to solve a problem, find a value for a function and so on and so forth. The tasks sort of remain the same, but because the input is presented to us in this stream, unless we store the stream in its entirety, okay, basically as the stream moves on, we have lost access to that piece. So this is a fundamental difference between the random access model and all. In an array sort of a thing, I can always go and look up the ith position. Here, what is the ith position? It's not at all clear, right? I saw a piece and it just went by. So in the streaming setting, you can choose to keep, so you are not expected to answer the question right as that each piece of information becomes available to you. You can wait for a while, and after the end of the stream, you can answer. So potentially, you could keep storing the pieces of information you see, okay? And that's where the space complexity, limited space complexity comes in. The challenge is to do it without storing the entire thing, okay? If you store the entire input, you're already using up order and linear space, right? So the question is, can we solve any of these problems? And we'll see some of the same traditional questions that we have asked ourselves or you know of in the default or the offline setting. But the question here is, in this limited in this different setting of the input presenting itself, can we perform some task? And supposedly we have an algorithm for the offline setting, then of course we can do the same task by basically storing the entire input and running that algorithm and outputting the answer. So here the challenge is to do it in sublinear space. So naturally you cannot store the entire stream. Okay, so that's is the thing. Now sometimes it may not be possible to exactly solve a problem without actually storing the entire stream. And there are results showing that. Now, we won't be going into all that now. Today, the goal is to just give you a very, invite you into this world of very different so just to give you a flavor of it. And I think Fahad set up the presentation very nicely by yesterday asking a question. Do you all remember that majority finding question? Okay, so we will come back to it. So formally stated, the input consists of a stream of tokens or items or objects that are seen by the algorithm one by one. Algorithm has limited memory, so M is the length of, so M is the number of items. Now some of these items could actually be duplicates, like the same item is seen again and again, okay? So M is literally the number of items you see, not number of distinct items, okay? And the space is, let's say, it's like a budget that you do not want to exceed. And that really the question is, how well can you do while remaining within this space budget? Okay. So where do you think we see such examples quickly? Where do you think this sort of a computation would find a natural application? Okay, you're not actually, you have not, you mean you have not downloaded the video, it's just directly streamed. Okay, but what is the computation we are doing there? We're doing some but okay. So that's not exact, the word streaming sort of seems like that, but the word streaming comes in from the fact that it's like a stream of data sort of coming through, okay? So right now, because of the way the internet works, we're dealing with very large data sets. And there's really not enough space to store it and not necessary to store. Much of that is junk. And we just want to be able to do fast computation with as little storage of data as possible and then reuse that space if possible. So that's sort of one of the things. One standard, somebody said something? Yes, yes, yes. Sure, absolutely. So if you have the budget B, okay, of space, if you see some data, some piece of information that you've stored is redundant, it's not useful, you do get rid of it. You can, absolutely. Okay, or you can update it and so on. That's all of that is up to you. Okay. Yeah. Sure. Yes, yes, exactly. So we can all sort of empathize or sort of appreciate the need to do things without storing everything on hard disk and sort of this thing, right? Yes. So we quickly run out of space. So network switches is something that there's a huge amount of data just passing through. And you just have to make some simple computational decisions about how to read out the data and so on and so forth. Really no need to store anything, you know? So that's one thing. Distributed computing, this is age-old sort of application. You have chunks of data stored, replicated, or like stored all across, split across servers. And you kind of have to take some from here, there, and do some computation and like the message. So that's another thing where streaming algorithm type of computation comes into play. Okay, so let's do some really simple puzzle-like questions so that you people feel interested, and then you can read very heavy-hitting, difficult papers and work on this subject, okay? So we have an array of m integers, okay? So it was yesterday's question without the fact that there's a unique element like that and so on and so forth. And there's an element, let's say, I don't know whether there's an element, but I want to decide if there's an element which appears more than m/2 number of times, okay? Suppose now this this data is not presented to you in an array, but you see these pieces by, okay? Element 1, element 2, element 3, and so on. How would you find such an element if a majority element does exist? Yeah, you people had a lot of the correct ideas there. So let's do a little more general there. Okay, so let's assume this majority problem is solved, okay? So let's say a little more. So you're given an integer k, and you're really trying to find elements that appear more than m/k times, okay? So if k is 2, that's a majority element, right? So suppose I tell you that no, I'm not so interested in a majority element. I want to generalize the problem a bit. For some k, I want to find elements that appear at least m/k times. How will I know which are the... first k or first k distinct? Okay. How will I find frequency? Okay, like a counter. Okay, and then? Now suppose I get a k plus first new element. I don't have space to store. Then, like you are keeping k different counters, right? For k different keys, correct? So let's call it keys, okay? Distinct values are called keys. And then what happens when I see the k plus first element? K plus first key? Only one element. So the thing is, so you're saying when I see k plus first element, I have to make space for this. So I have to remove something. So what will you remove? But will you not lose count of how many times it appeared? Maybe that's the case. Maybe that's the highest frequency element. So when I see that k plus first element, and I realize, well, the reason I don't have is because I don't have space counters, right? Empty counters to basically keep track of this. Then I go into my table. So think of it as an offline type of a thing, how we would maintain this table. And basically we can simulate this using counters on the fly, okay? So basically I go back to this. Okay, so this is the pseudocode, but let's just discuss in words. So we have, no, I should use iPad. Okay. Okay. So let's say counter 1, counter 2, counter k. Okay. Each of this is storing some value. There's a key associated with it and a running counter which tells me how many times this element associated with this counter 1 has appeared in the stream, followed by C2 and so on. So now this say k plus first element appears. I have no space for this. So what I do is go and decrement each of these counters. Okay. And I do nothing to this. And the whole thing again runs itself. Okay. And I keep doing this until I have basically, the stream has ended. At the end, okay. So each, so at the end, I have again these k counter spaces. Okay. See, one thing is there that next time after I have decremented these counters, maybe the next element that appears is this E2. This E2 is this corresponding to this counter. Okay. So again, I go and I would basically increase it. Okay. So this is the way it is going. Okay. Now, at the end of the stream, I have a certain counters. Some may be empty, some may be 0, or some may be positive. Okay. Now, so has the algorithm ended? Now can I say something meaningful? These are the, I claim, these are the potential high frequency elements. Okay. These are the potential high frequency elements. Potential. Now I actually have to go back. See, because of this increase and decrease and so on and so forth, I don't really know which of these elements exactly could have been the high frequency. Some of them could actually have appeared fewer times in the stream than I need, my threshold, which is that m by k, right? So the second pass would be basically check correspondingly whatever key I had stored in C1, how many times that actually appears. And this time I stored the precise value of the frequency of appearance of this element, followed by C2, C3, and so on. Okay. All those elements that meet this threshold, now I have this was a potential set. After this second pass, I verify, and I know exactly which of these would have been, was a high frequency element. only the ones that are for which I have, yes. Yes. Okay. Hmm. No, if it something becomes zero here, suppose, okay, C1 suppose became zero, okay? Then again another new element shows up for which there is no current counter. I can start saving there. If the yes, yes. Whenever there is an empty space, counter space, okay, the number of counters are like my budget, K. If I have a zero counter currently, I use that to keep track of the current element. But then I have to also update the key, okay? Because I need to know what counter this corresponds to, okay? So that's one thing. And so now, is the protocol first and foremost clear? How much space do you think this will need? Bits. See, this is in streaming algorithm, because we literally care about how much space we count, how many bits would it take to express even a number. The counters are integers, right? We are keeping k counters. Each one has a, yes, the number of times an element can appear is how much? M. Okay, that's the most, right? So the counter itself would be like it would take log m bits maximum. The keys, there are n distinct elements, let's say. So you need this many bits. Sorry? In the second pass, you're just keeping k counters, no? Okay, good question. So, sorry, I should have mentioned this. So when I explain what the streaming algorithm is, it was by sort of the idea was like, it's a single pass. Sometimes for this purpose of these algorithms, we can assume that we get to see the stream repeated again. So that's what a second pass, 3 pass would mean. Now, we would also like to minimize the number of passes. But sometimes in this particular algorithm, to get precise, accurate answer, we need the second pass verification. Because if we end with the first pass, right, what we have is a potential. So if there exists a high frequency element, it will be among the counters. That's all we can say. Okay? But we may not be able to say exactly which of those it is. So that's sort of the issue. In general, it's always a trade-off. More space you take, better quality solution you should be able to present. That's true for time complexity also, right? If I exhaustively use as much time as I need, I can always get the correct answer. But sometimes that is not needed. Yes, we will do this. So is the algorithm first and foremost clear? So, no, I will always have k counters. And depending on which, suppose the first k distinct elements are these E1 to EK. Some of them may have repeated before, like like maybe it's E1, E2, again E1, E1, E2, E1 like this. Suppose the first k, so the first C1 k counters will be allocated to these elements. If I were allowed to keep distinct counters, why am I deleting? I mean, I might as well just keep track of every, there are m elements, I might as well keep m counters, right? The idea is here, this log m by log plus log n, this is obviously sublinear. K is likely to be much smaller than m and n. Okay? This is the I'm saying that's a fixed thing. That's part of the input. So this is the thing. See, you're given that integer k. is given to you as part of the input. And your goal is to define an element that appears at least m by k times. That k. 100. Yes, that's what you just gave out the think. Yesterday, somebody here very nicely pointed out when we have a majority element, we had a 2n size array and some element was appearing n plus 1 time. By pigeonhole principle, there has to be consecutive positions where the number repeats itself. Now, if you don't have k to be 2, but something large, using general understanding of division, if an element appears, there are m number of items coming through, there's an element which repeats itself m by k times, then can you say something meaningful? How many distinct elements can there be? Right? More and more frequency, the higher frequency you have of elements, fewer distinct numbers you're likely to get. Okay? So that's why that was such a nice, precise example. For majority, it's very easy to visualize. But the same thing appear. Yes. Yes. If an element is appearing at least, if you have elements which is, yeah. Okay, sorry, I misspoke. You're right. Okay, right. So you can have one correct. Oh, sorry. Could be very large. Yes, sorry. Yeah. So you can have this, right? These elements are exactly the same. Okay, and all these are all, yeah. So you can have m minus m by k minus 1 total distinct elements, right? This many number of distinct elements is possible. Sorry. But what still remains the case is that if you have, so if I, instead of doing this decrementing counter, if I just kept track of these elements like this, I kept on writing how many times E1 appeared, followed by how many times this thing appeared, and so on. Then EK plus 1, by the time I reach this other element, right? When I delete this, perhaps there's a better way of explaining this. So when I'm doing this decrementing thing, what am I doing is that basically I'm taking down one entire row. No, I'm saying by row, each column represents a distinct element. The number of, the size of the column, like that, this column need not be all same line, it's okay. I'm saying the moment I see a k plus 1th element and there's no counter space, I'm basically, this decrementing a counter means what? It means basically I'm removing one row. Okay? So this, if this were to happen, okay, now I do this how many times? There are total m number of elements only. How many times would I actually be able to do this? Maximum number of times? What setting? This is just saying like if I, instead of keeping counters, if I literally were to save the elements. So this is basically what happens is when I have run out of counter space and a k plus first element appears. Then I'm decrementing a counter, each of the counters, right? C1 minus 1 here, right? So basically that means is I'm getting rid of, see, I don't store this new element anywhere. I just basically decrease the counters that I already had running. Some of them will go to some non-zero maybe, some might fall to 0 and so on. I never go to negative first and foremost, because a 0 counter means there is available space. Store this key plus this key for the k plus first element there and increase the counter to 1. Right? Okay. So now the point is when non-zero potential key is my handwriting key for high frequency element. Yes. And the second pass allows me to check which of these things is the case. Okay. All right. So, okay, let me just, how much time is there? I just wanted to spend some. Okay, so let me just go to some graph and then we'll come back to this. Okay. All right. So this was one of the things which is about numbers, and there are lots of problems which people sort of number-centric problems like finding frequency, moments, lots of other things, and so on and so forth, which deal precisely with numbers. Now, the other thing that we want to do on graphs, on streams, is solve graph theoretic problems. So now graphs are different from in the sense that you have a vertex set, an edge set, and so on and so forth. For the purpose of now, let's suppose we know the graph, the number of vertices in the graph are n. Okay. So what is unknown about the graph is the edge relations. So what comes on the stream are those sequence of edges. So the edges would be basically just telling me vertex 1 and vertex 2. So let's say first is this. So E2 is 2 and 3 and so on and so forth. Okay. And the vertex set is, let's say, represented by this elements from 1 to n. In some problems, we don't even know what n is, but it's okay. I mean, that's, let's suppose we know n and this. Now, obviously, you could do one thing is to keep an empty adjacency matrix of n square size and start storing bit 1 whenever you see an edge, right? But how much space would that take? That itself would take n square. So you don't want to do this. You want to be able to solve some problems, some very simple questions, while the stream is present, sort of moving across. You don't have to answer right then and there. You can keep some information that you think would be useful for you to answer that question. So what do you think is a property we should be preserving? And this information we keep is called a sketch. Of course, suppose the problem is, what happened here? Suppose, okay, I'll tell you what the problem is. Problem is, let's say, connectivity. Is the graph connected? Very simple question in offline setting, right? But in the streaming setting, how would we do? Yes. Spanning tree. So as the edges are presenting itself, I need not have a tree, but I can keep a forest. Is that what you meant? Yeah, because to have a tree, right, a spanning tree especially, I know n vertices are there, I keep n vertices, and as the edges pass me by, I can try to construct a tree. But step by step, as the edges present itself, I need not have a tree, I would basically have a forest. So then can you complete this thing? At what point should I be able to say, yes, this graph is connected? Yes, at the end, is this visible? Okay, I'm sorry. Yesterday, I watched the match and I didn't have time to make slides, so I did some screen grab and put some pseudocodes in here. I hope you will forgive me for this. Okay, so yes, this is exactly what it is. You maintain a forest. And at the end, okay, if you have a tree, you can say the graph is connected. Good question. How much space do you need here? Yes, but each node requires how many bits? Log n. So this would take n log n, right? Because I'm going to keep a spanning tree, I need all the n nodes, but each node representation takes log n bits, right? So n log n. Still better than n square, which would have been the case if I had kept the entire adjacency matrix, right? Okay, is this clear why if I find a tree, if f is connected, I know that the original graph was connected. See, this connectivity has this monotone property that if a subgraph is not, if I can find a subgraph which is not connected, right, then the original graph could not have been connected as well. Right? If a spanning subgraph is not connected, then the original graph would not have been connected. Now, what about the other side? If the graph is not connected, we cannot say anything about the subgraph. Okay, but how are we keeping this algorithm? See, how are we creating? It's not any subgraph, right? Sorry? Yes. Hold on. He probably was the first person. Do you want to say something? He's never answered anything, huh? Okay. So each time you basically keep, so this is why I keep log n bits, right? So it should probably be log. Now log n is okay. So n nodes, okay. Potentially edges are n square, but representing them is still log n, right? Okay, so I basically keep the information that, so I have all these n vertices, okay? So suppose this edge has come in the stream and I realize, okay, adding this edge is not creating any cycles. So I add it, so I keep it, I store this information that this edge appeared. Then some other edge appears, let's say this one, again doesn't create cycle. So again, I sort of keep this information. Then comes this edge, okay? So something like this, and then I see this edge. Oh, I see, fine, this edge is creating a cycle. I will not preserve this edge E4. How? Which information have we lost? We know this endpoint and this endpoint, they are there in the graph anyways. We also know, because we have stored these edges, E1, E2, E3, in our sketch, I know that this vertex is reachable from this vertex. So, right? Okay, I have not said anything about constraint on time. In whatever subgraph I'm keeping, right? The sketch is a subgraph. I can check which vertices are reachable from which using a path. So what I suppose you're asking is, the sketch, when E4 becomes alive, right? I know this is the subgraph I have. I can see the endpoints of E4. I check whether are these two vertices reachable in my current sketch. If they are, then I know adding E4 will create a cycle. Okay? So I don't do this. So this testing at least can be done easily using whatever information I have in my sketch. So why do you think for a connectivity property, is it okay to ignore cycles? Correct. That's the point. For all of these graph algorithms, what we are trying to do is, or for the matter, any problem, we are trying to preserve some minimum amount of stuff that preserves the property we are trying to test. So here, connectivity, I don't need cycles, right? All I need is paths. So if a path already exists, why bother with the cycle? Okay, so, all right. So this is something that you can easily show that this will actually give rise to a correct answer, okay? All right. How would we do depth first search? But if it's not, suppose at some point I get an edge like this, it's not connected to anything. Right? So this is why, see, we know many different algorithms to grow a tree or maintain a tree, right? But this sort of Prim's Kruskal type thing is a very greedy process. It allows us to do things without not knowing what else is happening elsewhere. This is why you will see this sort of an idea coming through again and again, because the amount of information I need, it's a very local sort of a thing. Okay, so why am I not able to? I don't know why this one. Okay, so right. So I should say this thing that we just now did is an n log n time algorithm. We just saw, right? N vertices, and I'm keeping edge information. There can be n square edges, but log n amount of bits needed to store each information. It turns out that this is actually, this should not be this omega, it should be this, sorry. Okay. But this needs a reduction and communication complexity and so on. So we will not be going through. So what this means is this algorithm is basically asymptotically tight. Is it clear? That I take n log n to run this very simple algorithm, and there's a lower bound that says that this much amount of bits would be needed. Otherwise, some complexity theoretic assumption or conjecture will fall through, which is unlikely to happen. Therefore, this is supposed to be the lower bound. Okay, so this sort of result sort of tightens, bookends these kinds of algorithms, saying that, okay, they're as good as you can get. Edge connectivity. Do you know, also called connectivity? But okay, I sort of, do you know this problem? So you have a graph. It's supposed to be a very highly connected graph. Just, okay, what is the connectivity of a tree? How many edges do we need to delete to disconnect it? Correct. This is why tree is a minimally, sort of minimum, very sparsely connected graph. But the kind of graphs we are talking about, let's say, requires removal of k edges to completely separate them. So separate meaning there will be two sides of the vertices, and the edges, basically, the ones that you have removed are these. So basically, there are no paths that connect vertices from this side to this side. Okay? All right. So this is also what one would call a cut. It's important to sort of keep this sort of a thing in mind. So what this means is when you have a graph where you need to remove at least k edges to disconnect it, what can we say about the size of the cuts? Min cut requires? Right, so the min cut size, every cut is of size at least k. Okay? All right, so now what do you think, should I do to answer this question? Very similar to the tree, to the connected thing. This is a one step further, right? That was just connectivity, maybe one connectedness, two connected. This is like a little more. So perhaps we can repurpose some of the same ideas that we saw there. Yes. K forest, correct. And sorry? Good. So I will keep K edge disjoint forests, right? And at the end, what should I test? Connectivity, right? Okay. So this is it readable? Okay, I'll just say. So start by keeping K sets, start by empty. So any edge that appears, so if you have a possibility, so initially everything is empty. So when you see K edges, whatever the first K edges, let's say, you can put them in any of those, this thing, the K sets. Now, subsequent to that, you will basically see an edge when it comes to the stream. You will see if I adding to F1, will it create a cycle? Okay. If it doesn't, you add to F1, right? So because we are growing a forest, right? So we cannot allow cycles. If suppose F1 creates a cycle, then you try for F2. If F2 creates a cycle, try for F3 and so on. Okay. Now, do this until, the stream has run out. Then I check if this set, that this is what should be a disjoint, edge by edge disjoint thing, okay? If this together, this set of forests that I've taken, the union of this, if this is K connected, like this. So what should you do then? This would be a cut edge, right? So then you don't add that. That is sort of the important point. So why do you think that this information that we are keeping, K forests, right? Why is this sufficient information for me to keep to answer the original question? One direction should again be very obvious. See, this F, it's a subset of G, right? If itself is K connected, G must also be K connected, right? If you have a subgraph which is densely connected, so the bigger graph only contains those edges and some more potentially. So that should also be K connected, right? So this direction should be obvious. Correct? Because of the same property as we saw that connectivity, this subgraph property, if a subgraph has that property, if subgraph does not have that property, then the original graph need not have it. But the point is the other way around, it's true that for a graph to have that property, all of its subgraphs should have it. Okay? Sorry, I said the other way around, sorry, yeah. No, what I want to say is this, I'll confuse the contrapositive. So if a subgraph is K connected, let's say if a graph is K connected, then a supergraph, right, is also K connected. This follows from the definition. Okay, so what about the other direction? Need not be true. So, okay, so you're saying that you can have this property that a large graph is K connected, but a subgraph is not K connected. That's what you're saying, right? Yeah, that's the thing. Okay, fine. That's true. But for this particular thing, this is a specific subgraph, right? It's not any subgraph. So why should it be that if this is K connected, this is also K connected? Yeah. State, how so? Yes. So this sort of thing. Then what are k paths here? But what is the k path here? You're referring. But you have to prove this, right? Say G is connected, but F is not. Yes, we have to prove that. Okay, so suppose, so then where is this, like, are you assuming that suppose F is not, then I will show a contradiction, that sort of a thing? Okay, yeah, okay. Fine, then let's continue. This is again stopped. Tell me, okay, so you start with those, a family of k edge disjoint paths, then, sorry. Okay, you can think of it and tell me. This is rather fairly straightforward. Anybody? See how the graph, how this particular algorithm processes each edges that it comes across. No. No. FIs are each forests. Yeah, the union can have cycles. Sorry. Oh, F. Sorry. Yeah. So, okay, say F is not. So it means what? There exists some cuts, right? F is not K connected by when I say, right? So this graph F, right, has a cut S, V. Remember, F is a spanning subgraph, right? So the entire vertex set remains the same as G. So this is this, and the number of edges here is strictly less than K. Okay? That's what not K connected means, right? That if I can remove these edges, I have disconnected the graph. So now what? But G is K connected, right? So this thing, this cut cannot be a cut for G, meaning G has an edge going across. Yes, no? So this exists in the edge set of G, but not set in F. So when this edge must have presented itself in the stream at some point, right? Then what happened? I could have added this edge to one of the FIs, correct? Is this clear? But, and that's the contradiction. No, meaning the edge sets in F1, F2, they are different. This is why we are able to say that there exists an edge in G which does not appear in any of the FIs. Therefore, E should have been, when E appeared in the stream, our algorithm would have added E to one of the FIs where it could have been added. Is this clear? Okay. Should there exist? added. Okay. So, do I need to say anything more or anything differently? Okay, just think about it. These are fairly, this is how all these spanning tree algorithms, correctness, and they sort of go forward. Okay, now let's talk about bipartiteness. Given a graph G, how do I test it is bipartite? Again, how? But this we have to do it in the streaming setting. So, okay, so you are using the two colorability property of bipart. Okay, the point is, see, when an E1 comes in, okay, it's the edges that are coming in, right? So I say, okay, so far, if it is bipartite, they must get two distinct colors. So I do this, okay? That's what you're saying? Now I get another edge at some point which has like this. So then what do? This is 2 is known, this one automatically gets 1. Okay. And then how many edges do I store then? Sure, but he's saying, say, break, that's another point, right? So some other edge comes in. Maybe later on its adjacency, I say, oh, this is 1, this is 2. But later on, I learn about this edge, and the adjacency really should have been 2, this should have been 1, right? So that's another thing. But this is also there, that to do this, right, I would have to sort of keep all sets of edges to keep this coloring property. So while that is a if and only if condition, it's a necessary and sufficient condition to capture bipartiteness, maybe it won't work in this. Think in terms of connectivity, because as we have seen, the connectivity property is testable in the streaming setting by basically keeping forests. So maybe we can tinker with that. Yes. So bipartite graphs have cycles, they just won't have odd cycles. But as we have seen, its cycle detection is easy in streaming, right? I keep on adding edges until I can see, okay, a cycle is emerging. Here, we will not just discard something, like if I see a cycle, but it's an even cycle, it's not a violation. Yes, we can just immediately say this can't be bipartite. So here, preserving bipartiteness in my sketch basically boils down to testing for odd cycles. Right? Okay, so the pseudocode is rather straightforward. This. So anytime you have an edge UV that appears, check if the forest you have kept so far, adding that does not contain a cycle. If it does not contain a cycle, then just add to your forest. No harm. If it contains an odd cycle, you can just terminate. If it makes an even cycle, ignore, like we were doing before. Sorry? Right. Okay. So I did not discard. Yeah. Correct. So yeah, what you're saying is this basically. So this is an edge that I ignored. Now, yeah, and later on, there are some other edges which are presenting itself like this, right? Suppose this thing. If I had kept this red edge, I would have detected this is a cycle. But I kept all these other edges for which the reason I didn't keep this thing cycle was because I kept all this other odd length path, right? So this odd length path plus this, suppose, okay, let me just, but yeah, you're right. It needs some more argument. So suppose this is the way it was. Now let's say, no, this is E4. I ignored E4. E5. Yeah. No. He's saying if you detect an odd cycle, you're definitely sure it is not bipartite. The question is, were we able to detect all the odd cycles? Because we didn't keep all the edges, that's the thing. So, okay, yeah, it requires a thing. Okay, so, sorry? Yeah, please.
Suppose that these edges came before and we have removed this edge.
Yeah.
Now these edges came, so it does not form a cycle. It also forms an even cycle.
So I
Then we
ignore
have
this.
With this we can have an odd cycle.
Right. That's the sort of thing that he's saying also, that I ignored these things. So when this edge came, but when this edge came, I didn't add these or these, but when this edge came, I realized that this is an odd cycle. So, okay. So the reason I didn't put some edges were because, and my algorithm has not terminated, is because I found an even cycle, right? That's the thing. So an even cycle would mean that the two endpoints, let's say from V1 to VT, this is an odd length path. And then some other edge came and it became even length path. So I suppose this would be proved by a parity argument, that if at the end I couldn't have missed an odd cycle, right? So at some point I didn't add this edge E4. I added the edge E5 because it was safe, right? And then when if I ever have to use this portion of the cycle, it would have to, if this path gets used, it would make an odd cycle along with the older, this V1 to VT. Yes. Path. But from a cycle edges missing, it should have been a path. Why would I get a walk? This thing that I skipped. Yes. Okay, suppose it's a walk. All right. So suppose like this, it comes back. Okay, then. Okay, so for every edge E, which is not in the sketch, it is not in the sketch because it was forming a cycle, right? It was forming an even cycle. The question is, suppose there is a possibility that after addition of all the other edges along with this E and some of all those other edges, so say P2 and E together form a odd cycle. And because E is not present in my sketch, I didn't detect this. So this is the thing, right? So every edge that is not in, suppose there exists an edge which is not in the sketch, okay? But there exists a path, P2, that connects the two endpoints of that edge, such that P2 and that edge together make an odd cycle. These are the type of odd cycles that would not be detected in my sketch. When I add any of the edges of the P2, this is when, if I had kept E2, when I was adding the edges for P2, I would have seen, well, this is creating an odd cycle because E is not present in my sketch. So this forbidden structure wouldn't present itself. Okay? And therefore, this is a path. This has to be a, because this is the violation, no? There has to be a path connecting the two endpoints of E, which is basically creating an odd cycle. How much are we doing time-wise? Time over? Okay, let's discuss this over. How much? We have a break of, sorry, Rohit is the next speaker, right? Okay, so I'll be here. Let's talk over this. Okay. Sorry.